even though I said 2 minutes, I'm not sure there's a huge point in waiting. I will make the introduction. So, Werner Nahm, of course, needs no introduction to this audience. He's been here as one of our faculty members for a year and is an emeritus professor here at the Institute. He's more famous for having his name in the title of papers than in the author, I think.
Yeah.
Which is a remarkable.
Thank you. My aim is very limited, and it's actually rather for mathematicians than for physicists. I want to give a short answer to a question posed by mathematicians: what is a quantum field theory and what is a field? Now, I've tried that various times over several decades and only had success within the past year, where some mathematicians really liked my answer. And so I give the answer informally. I'll say a little bit about weak rotation later, but for the moment I'm mainly staying in the Euclidean context. And the answer will be a functor from a Bordison category to a vector space category. So, quantum field theories work in a particular dimension, so that we call the dimension n. And for a category, I have to tell you what are the objects and what are the arrows. So, the objects of the Bordison category smooth n-1 dimensional manifolds, and the arrows well, there are manifolds, n-dimensional manifolds, of course. Compact, but in general with boundary. With boundary. And so, if you have objects B source and B target, then an arrow is a manifold M such that the boundary can be written as a disjoint union, where the terms may be empty. And you have an isometry BS B1. Okay, so isometry, which means that my manifolds have to have a metric. Suppose they have a Riemannian metric. So this is a pretty well-known category. Mathematicians know all about it. I won't use collars, and that means that, for example, if my n is 2 and I have a boundary which is a circle, I can cut out a circle in a plane, and I can have a cylinder. So I can glue the cylinder to the plane so I get a crease. This I allow. And so my manifolds may have creases, but I suppose for simplicity for the beginning that I have a category which includes all smooth manifolds M and is the smallest category with these properties. So I only admit creases in the interior of the manifold which come from gluing in this way. So these manifold categories, well, of course, firstly because my manifolds have a metric, the space of errors from given source and given target has topology. So later my factor will be continuous. And in fact, it even has a metric. And another obvious property of this category is that it is monoidal with an operation just disjoint union. Of course, I can take disjoint union of manifolds. Monoidal with respect to disjoint union. And the unit object for the monoidal is the empty set. So I include as possible objects also the empty set. And my manifolds are not oriented, so a priori I don't know what should be the source and what should be the target, but manifolds are, categories are set up in such a way that you know what's the source and what's the target. So I need an operation which can move a component from the source to the target or vice versa. So if my source boundary is a disjoint union, it's true, then I can move one component from the source to the target. So then I have an arrow which goes from the BS2 disjoint union to the target. So these are all the operations I need. Disjoint union, the empty set, and some adjoint operation which moves a boundary component from the source to the target or vice versa. So my vector space category, well, I don't have to say much. It's vector spaces with linear maps. And in the Euclidean context, actually the more natural thing is to use real vector spaces. The imaginary numbers usually come in by the recruitation. So when you write down a Euclidean quantum field theory, in many cases you never need to talk about complex numbers. So let me stick to real vector spaces, and I need real self-dual vector spaces. So, for example, Hilbert spaces, and that's all I need for the unitary case. But when I want to generalize it to a non-unitary Euclidean field theory, then I can have spaces which are, well, I think that's even the general situation. Direct sum of two Hilbert spaces, but for one of the terms, I change the sign from plus to minus for the metric, for the scalar product. So that, of course, still would be a self-dual because the individual spaces are self-dual, and the sign of the metric doesn't matter.
You mean the sign of the metric in the Hilbert space?
Well, my scalar product in the Hilbert space, I multiply with -1.
So it's a Klein.
Pardon?
Klein space, is that what they're called?
Well, that in the adjoint operation, I would have a minus sign.
Okay.
Just. So that's again a monoidal category. Now with respect to tensor product. And again, I have a unit object, which is just the reals, because whatever, that's isomorphic to H. And again, everything is topological. When I have two Hilbert spaces, I look at the maps. So for me, a quantum field theory is a functor from here to here, which preserves all the properties. So it's a continuous functor, and well, I denote it as Q for quantum, and so when I have the disjoint union P2, then it has to give me the tensor product of the spaces. And when I look at the unit object here, the empty set, then my vector space is just the real numbers. So now I want to show you how the standard structures of quantum field theory follow from this axiom. And so I make a list, start with the partition function. And I say something about unitarity. And states and Hamiltonian. An example, which of course is free quantum field theory, free scalar. And then I define in that context what is a field, and in particular the energy momentum tensor, the mu, and well, specialize it to conformal field theory and say something about the motivations. So it's just the standard thing you would do in any textbook on quantum field theory. So when I have a manifold with no boundary, empty boundary, then this will be an arrow from the empty set to the empty set. And so manifold empty boundary. And when I apply my functor to it, I will get a map from R to R, because my functor takes the empty set to the real numbers. And a linear map from R to R is just a real number. So that will be my partition function, which I call it in the usual way, set of M. And then I want to construct my state space for an n-1 dimensional manifold B. And I want to show that when you know the partition function, so the value of the functor for manifolds without boundary, then you know the whole theory. So when I have some n-1 dimensional manifold B, and I want to look at the states on B, then I take particular manifolds, the Cartesian product with an interval, and then I get a semigroup because I can join intervals. So I get my functor applied to such a manifold will be a map QB to QB, parameterized by the length of the interval. So T2 minus T1. And these maps will form a semigroup, obviously. And the next thing one has to show is these maps are trace class. So I can diagonalize them. And for that, I need continuity, firstly. When my interval converges or goes in the limit to 0, then in the limit I get the identity map. Because it's clear when I have here a boundary B and I glue in a very short cylinder, take the limit where the length of the cylinder goes to 0, then nothing happens. So for t goes to 0, I get the identity map. And next, I use my duality operation. So that means for my cylinder, I regard now both boundaries as, let's say, incoming boundaries. And so I get the dual of the identity map. Now, when I have an identity map on my vectors EI, I go to EI, and I take the dual, well, that's linear algebra. So I get sum which is trace. And because from my setup, when I have here such a manifold, and I glue together the two isometric boundaries, then I get another manifold which is, well, it's a manifold without boundaries, so I have a well-defined partition function on it. So my maps here are trace class maps, and moreover, I have no orientation, so I can switch around the interval, so I can diagonalize. They are symmetric. Of course, if I would have a direction, then I might have Jordan blocks. But so I get here a trace class, and my semigroup is generated by a Hamiltonian corresponding to the given boundary. So for any n-1 dimensional manifold, I get a Hamiltonian. E to the minus Hamiltonian corresponding to B times G. And trace class. So my spectrum is, in particular, spectrum is discrete, and the eigenspaces are finite dimensional, and well, their multiplicities don't grow too rapidly with the eigenvalues, otherwise my trace would not exist. So now, when I want to construct the vectors in this space, then I look at all manifolds which have this particular boundary, and I glue in a cylinder of variable length, and when I have a partition function, I get a function of t, where I look at the Laplace transform. So that will be some sum. So here, let's say M1 manifold M2. And here, this thing by the usual GNS, Gelfand-Nahm-Axiom method, I construct a vector space on the finite dimensional multiplicity spaces, so for eigenvalue EI of the Hamiltonian. So now I have a Hamiltonian, I have states, and I can make a Wick rotation if I want to go to the corresponding theory in Minkowski space, as long as, well, my Minkowski space is just a Cartesian product with an interval, which is of course a big restriction. And then the difficult work would start. Do you have an infinite volume limit? These things, all the really difficult part of what Klim and Jaffe have been doing, for example, when they constructed the quantum field theory. I'm not going to talk about that. I'm not doing anything difficult, just defining concepts which you can explain to a mathematician. And the way unitarity comes in is if you look at singular manifolds, so let's say manifolds which touch at a point, then in the unitary case, you just get the product of the partition function. Whereas for non-unitary theories, in the limit, things would diverge. Maybe I'll come back to that later. So in the unitary theories, I can enlarge the possible spaces for the manifolds, but there's nothing which forces me to do it.
Where would you see the renormalizability of the theory? Because it's that clear to me that the Hamiltonian is well defined to begin with.
Well,
without regulating.
If you ask it the other way around, for example, what do I expect? Which things you know from nature would satisfy the axiom here? So an SU2 theory, which is asymptotically free, should fit in, and a U1 theory presumably would not fit in. So it just would not satisfy the axioms here.
Is the Hamiltonian self-adjoint?
Well, from the axioms that follows the existence of a Hamiltonian. So if you have a system which is not renormalizable, I don't know if there would be cases where you get some non-trivial fixed points so somewhere else, but certainly if there's not the fixed point you are expecting, then the axioms are just not satisfied. So in that sense, well, some
one action.
Yeah.
So far, I've seen only one action, but you have a functor.
Yeah, I certainly can't write down an axiom, an action from the axioms here. So I can write down, okay. What I can do, the usual thing one does, one goes to free fields and one does perturbation. That I definitely can do. So first, let me write down a free scalar field for the other. Yeah.
It looks to me like you could do something simpler. You would take piecewise linear manifolds and try essentially. I think everything would go through, and you would have set up a lattice theory.
Actually, the whole thing, of course, is in a way inspired by a lattice theory. I come to that immediately. So for free scalar fields, I can explicitly write down the partition function for a manifold without boundary. It's just the determinant of Laplacian for the given metric, positive Laplacian, plus n squared by mass to the minus half. And of course, the way you would get that on the lattice, you would discretize it in the usual way. So here I would have, in the continuum, you would have a gradient squared plus m squared phi squared integrated over the volume, and you can discretize it in the obvious way. And actually, I would be very interested to have some contact with some lattice calculations, because mathematicians tell me that they would have a great interest in people telling them how to calculate these zeta function regular as determinant. They were introduced by Singer, and then Hawking talked about them explicitly for physics. And mathematicians said they are, in general, they are impossible to calculate. And I tell them, for lattice people, it should be very simple. The only problem is, last time I talked to people here from the Trinity lattice group, they would be very reluctant to go to a metric which is not flat, because they don't know how to regularize their integrals. But I don't think it would be difficult. I mean, what you get here is you have the differences of the lattice. Phi squared, and leave out the n squared. And then on the lattice, then you get some power of a, basically exponent given by the number of points. But you could easily generalize it by some exponent of a finite number of terms, and one would have to check how many terms, some exponent of I times some coefficients which depend on the metric, assuming curvature. And just take the minimal number of points such that it converges and it goes to zero.
People have done this. In Simon Cattell's group, and what's the guy in there?
I'll ask you later about the literature, because that's, well, mathematicians are not aware of it. And so one easily could check these things, because they are symmetric spaces for which the determinant has been calculated. So one could easily put the thing on the lattice, calculate it in these specific cases, and see how good are the results. And I think it would be an excellent mathematics publication. So it's really something the mathematicians I have talked to would regard as very important, and according to their opinion, beyond current technology, which is nonsense. So, well, for this partition function, of course, you can get the usual thing, and you construct your state spaces, which exactly what comes out, the usual Fock spaces, and whatever the creation annihilation operators. But let me tell you what are fields in general, and how also for this case, how to get out all the fields. And so in words, fields are projective units of states. So look at annuli, any dimension. With a common center. Then they form a directed system, because, well, when annuli fit together, you can clue them. And so you get a directed system. In this case, I take the maps from the inside to the outside. And I can take projected limits. Physicists usually have not looked in detail at the mathematics of direct limit, projective limit, and so on. But it's really something you learn in elementary school when you first hear about pi. I mean, what is pi? Well, 3.14, whatever. Okay, and you have an operation of rounding, which goes from an expression with many decimals to an expression with less decimals, which for mathematicians would be a projection to a smaller space. And the value of pi would be the projective limit. So for every given number of decimals, you have one expansion, and from someone with many decimals, you can go to one with fewer decimals by projection. And that's what I do here. I consider states on my spheres, which are linked by the arrows in my functor. And I define fields as projective limits in this sense. And of course, there are many fields, and I want to look at the most important fields one by one. And the most important ones are those of small scale dimension. And then, I have my projection here, and I have a map from a field to projection. A sphere of a given radius, and so for any radius that goes to a VR, which is inside here. And I look at my norm, and if that is proportional to r to the minus d, I say my field has scaling dimension d. So that's the main reason why I need a norm in my vector space. And in the non-Euclidean case, I have to be careful, because my norms tells me that I'm in a Banach space, and when I have a scalar product which is not positive definite, I have to be careful. But I think that in practice that doesn't really matter, because the states I get on the boundary seem to be, from the cases I understand, even in the case where I have non-definite signature, they all seem to be in one sector. So I get positive norms, and I never seem to go to zero. In the few theories where I have access to that, it seems to work out. but that definitely needs more research. Even in conformal field theory, it would be a theorem which is not so very easy to prove. Presumably true, but one really would have to work on it. So, in the conformal case, of course, a system of annuli with the maps is conformally equivalent to a system of cylinders, just by taking the logarithm. So my scale transformations here just would go into translations the way you know it from conformal field theory. So the whole thing which I wrote down here in the conformal case is just the field state identity. And here, you might argue about if the theory has a scale invariant limit at short distance, which is certainly true in the asymptotically free case, then it's basically the same. I just mimic a field state identity. So, the most important field is perhaps the energy momentum tensor, certainly in the conformal case. And I think it should be called the Hilbert field, because that's something Hilbert saw in 1950. There was this big competition between Einstein and Hilbert about general relativity. So Hilbert had invited Einstein to give a talk in Göttingen. When Einstein was working on it, and still was quite far from his equation. So he knew about the Ricci tensor, but did not know about the -12 g mu nu r term in the equations. And Hilbert didn't find that immediately either, but he immediately understood that Einstein was onto something big. And he wanted to have a part in it, which seemed to be reasonable because the theory was not complete at that time. And Einstein desperately wanted to do the whole thing alone. But on the other hand, he needed a good mathematician. And so they exchanged postcards every week, essentially. During the First World War, the postcards always arrived the next day. And on one occasion, on a postcard, which unfortunately has not survived, Hilbert must have told Einstein that, it has been stupid, the whole thing should be given by an action. And the action obviously should be the Riemann scalar for the gravity part. What else? And then Einstein did the variation and found -12 g mu r term, but he didn't want to give a credit to Hilbert. So, but when you know the answer, you find a way how to derive it with action or without action. And then he published his paper without citing Hilbert. And Hilbert published a paper where he put Einstein at the same level as me, even in the title. So Einstein had done great work in gravity, and me has done great work in electromagnetism. They're comparable. And they got very angry at each other for a few months before then they decided to stop this childish behavior and were friends again. So, but in Hilbert's paper, the Einstein-B stuff, he had a footnote where he said the obvious good way of defining the energy momentum tensor is as functional derivative with respect to the metric when you go to flat space. And of course, at the time, he took the derivative of the action. Now here, when you have a partition function, it's an average over e to the minus the action, and so you get the expectation value, or the one-point function of the energy momentum field, but it's the same thing.
What action did he use? Did he say?
No, it's just stated it works for, he said it works for any theory, for any reasonable theory. And that was the great thing about this paper. Of course, the me theory, that was completely red herring. It's a wrong theory, non-renormalizable theory. Me didn't even worry about the quantum mechanics.
I was wondering if he understood that it was the action of matter that gave the stress energy.
Yes, he understood that. And he did that explicitly in the example of the me theory.
Okay.
But he said it can be done in general.
Mm-hmm. Okay.
And so, of course, here, what I had by annuli, I had everything flat, but I can take my functional derivative with respect to the metric, and then I get here my energy momentum tensor, and I can see that the dimension here of the energy momentum tensor will be the space-time dimension, because when I'm working at a particular radius, and to get an effect of order 1 by a small change of the metric, I should change the metric everywhere, just a little bit, and so that would be my change would be the volume times the average over the functional derivative of my state. So you see that the functional derivative, that would be order 1. So the value of the functional derivative evaluated here at the boundary would be volume to the minus 1, which is clear. So these things work out very nicely, and it gives you the Virasoro field in conformal field theory. Conformal field theory, the axioms, if you want the vertex operator axiom, the only thing basically you have to add is conformal invariance, and that you can formulate when you have you scale the metric in a two-dimensional case. So the partition function is just your old one times one anomaly factor integral u sigma, and here you have the Gauss two-form, Gauss curvature for the original metric plus for the rescaled metric. when you work it out, that's fine. It gives you the necessary cocycle. And when you plug that in, then you get all the conformal field theory stuff. So perturbation theory, the one thing what one would like to get is for any small perturbation, the field which generalizes it. So what one would like to have is when you have some perturbation parameter, the derivative with respect to the parameter would be given by the one-point function of a certain field. And in the lattice case, that's really very easy because when you write the whole thing in the lattice, you have it a sum over products, and when you take the derivative of the products, it gives you the derivatives of the individual terms, and you sum over all the possibilities. So you explicitly get, of course, a discrete approximation, the field which gives you the perturbation. And here, well, I'm not quite sure at the end, people might want to look at manifolds with corners. Like when you have a manifold, let's say with a cubic boundary, and you factorize your boundary states into the different faces, then you're basically in the lattice context, except that here it's in infinite dimensional. But I'm a bit afraid of things which might happen at the corners. So what I think works is when you want to change your parameters, you fill out the whole thing by circles, and you know how to change boundary spaces here for the circle, because that's just, well, before I had quantum mechanics, and now just I apply quantum mechanics perturbation theory. And so then my field, which comes out, just comes from the quantum mechanics part, and I can construct it explicitly. So that should work out. And of course, mathematicians tell me some real mathematicians should get involved and do real rigorous proofs, but it looks promising and in fact not too difficult. So let's see, in particular the non-unitary case, one should think about it more, because I'm not aware of lattice calculations for non-unitary theories. And when one really understands what's going on, that should be possible.
So what do you mean by non-unitary? Because so far you're only looking at real.
Yes, so for example, when you take the 2-5 minimum, one knows the partition function on the cylinder is Rogers Riemannian. so the absolute square of the two Riemannian functions. And one can calculate it for any genus. And so
It's Lee-Yang-H singularity.
Lee-Yang-H singularity, exactly. So can one?
But that's also the complex plane.
It's complex. It's out. That's the problem. The non-unitarity in that sense is out in the complex plane. You can have complex action.
Yes, and so one thing which people write down is I find.
Where does the complex come in?
Well, when people describe it by Hamiltonian, then apparently they are, or by an action, then they are forced to put in i's in the action. And that, of course, prevents any reasonable lattice calculation, because you sum terms which vary all over the place, positive and minus, negative, and so on. So that's certainly not a good way to do the calculation. However, the result is perfectly straightforward, and mathematicians like it because everyone likes Riemannian, modular functions, and already the genus 2 case is mathematically quite intricate. So it would be really nice to put it just on a small computer and to calculate it. But so far, no one knows how to do it. Well, that's all I have to say.
Thank you very much, Werner, for. Let's open up to questions.
I have a couple of questions. So I guess that in the case you want to add those fermions to the story, you have to introduce a spin structure. There will be some topological abstraction, right? So like to define Stiffer width invariant. I mean, everything has to be put in a way that, I mean, there are, let's say, most constrained topology to allow to have fermions, right? Even for the CFT story.
Yes, that's something I have not talked about. I mean, fermionic fields are not fields in the sense I just described, because you cannot determine their sign. Whenever you have a global symmetry, then the only things you can define in a straightforward way are symmetric ones. But what one can do is to introduce bilocal fields. So, well, a standard way to introduce new fields would here be to generalize the derivative with respect to the metric, but instead of just changing the metric in a small way, you might plug in a small manifold, which might have holes, whatever. And you can generalize that to inserting a manifold with two boundary components at two different places, and then you would get a bilocal field. So for the fermions, what you can define is to have a bilocal operator, and then you have to factorize it. Now, in category theory, there is a way mathematicians invented a long time ago for this construction, and the people from algebraic quantum field theory know about that. That is Banach trying to write. And so when you want to, for example, describe the standard model in this frame. Well, or rather, forget about the U1 and look at the asymptotically free part. You know how it works at small distance. The theory becomes free, but you look only at the gauge invariant quantities and at small distance. The gauge invariance becomes a global symmetry. So then you can use this Tanaka-Krein stuff, and Friedenhagen was here, he knows all about that. And then you get, in a sense, the field of the standard model basically by factorization. And then you can put in the interaction terms. But that's a part of mathematics which is very well known, but I have not really learned yet.
Are there questions online? Just keep our online participants. Yeah. Arthur is still there, so. Or. Perhaps not. Yeah, perhaps there are no questions. So Iran is there as well. So. Okay.
Go ahead.
No, so in this higher genus case, you said it's much more complicated to consider higher genus surface and the axiom. I mean, it's much more involved. But I remember there is a sort of mapping between higher genus surface and hyperbolic space, right? Because by going the opposite of hyperbolic space, you can get something that is.
And of course, in a way, an open question, though one supposes one knows the answer, is apart from the free theories, what's the maximum dimension? And I'm not even sure if the six-dimensional conformal theory fits in here, because I don't know if I would be able to put it on arbitrary six-dimensional manifolds. So maybe the whole thing is limited to 4 dimensions, except in 3 cases, but I don't know. I mean, higher genus is doable, and for the young edge-regular 2.5 minimum model, I did it at least for genus 2, but the mathematical structure is really intricate, as you say. But it's Picard-Fuchs type equations, so integrable systems of ordinary differential equations with many components. And when you see them, then it's not obvious that they are compatible. They look quite non-compatible initially, but they become accepted.
We can thank Werner again, and he's around. Please stop the recording.
So this, at least in 2 dimensions, I know that this hyperbolic space, there is a discretization.